This is the second page of the Chapter 1 Limits Test Review Worksheet 2. Number 6, we have piecewise function here. F of x equals x squared minus 7x plus 10 over x squared minus 25 are the lines x equals 5 and x equals negative 5 vertical asymptotes. Justify our answer. Well, if we look at this the first piecewise function here, we know x squared does not equal to 25. What we can do is we can factor the numerator and denominator to get a better picture as to the behavior of some of these factors. So if we factor the numerator, we get x minus 5 times x minus 2. Factor the denominator, we get x minus 5, x plus 5. The x minus 5 will cancel out. There's a match, which indicates that the whole occurs at x equals 5. The factor that does not cancel out from the denominator indicates where the vertical asymptote is. So there's a hole at x equals 5, and there's a vertical asymptote at x equals negative 5. Okay, so that's part A. Part B, identify all horizontal asymptotes. To determine horizontal asymptotes, we simply need to evaluate the limit as x approaches infinity for our expression. So if we evaluate the limit as x approaches infinity, that's the same thing as evaluating horizontal asymptotes, where we compare degrees between numerator and denominator. Degrees match, so therefore we simply take the leading coefficients. So 1x squared over 1x squared, 1 over 1 is equal to 1. For rational functions like this, doesn't matter whether we go negative infinity or positive infinity. There's only one horizontal asymptote, and they will agree at y equals 1. Is there a value of a that makes f continuous at x equals 5? Well, there is a hole at x equals 5, and that hole is going to occur at whatever the result of this limit is. So if we evaluate the limit as x approaches 5, we get 5 minus 2, which is 3. 5 plus 5, which is 10, 3 over 10. So 3 over 10 is the physical location where the hole exists, and if we let a equal 3 over 10, then that will nicely plug in the hole with that ordered pair, 3 over 10. Part D, is there a value b that makes f continuous at x equals negative 5? At x equals negative 5, there is a vertical asymptote. If there's a vertical asymptote, there's nothing that we can do to make that function continuous. So therefore, we say that this is a non-removable discontinuity at x equals negative 5. Okay, number 7, if f is continuous at 1/8 and some values of f are given, which of the following must be true? We have a continuous function, and we see some of the ordered pairs that exists along this curve or along this function here. So circle all that apply. Fx equals negative 3 as the solution at 1/8 or between 1/8. It's telling us that can we guarantee that the graph will hit a y value of negative 3? Well, we see a y value of negative 2, but we don't see any y value below it. It's possible that this graph could dip below negative 2 and hit negative 3, but we could sketch this graph as well without ever hitting negative 3. So because the graph never reaches below negative 3 and never hits negative 3, based off of these ordered pairs, we can't guarantee that the graph has a solution, even if the function is continuous all the way throughout. Okay, so we have to take out the first option. Okay, f of x equals 0 has solution 1 in interval 1/8. F of x equals 0, so y value 0. We can guarantee a y value 0 because we see a y value negative 2, and then we see a y value 4. In order for the graph to continuously to be continuous and connect from negative 2 to 4, it's going to have to cross y equals 0 at some point, because we're told that the function is continuous. So this checks off, and we know that we can guarantee this. Can we guarantee that the graph will have a y value of 9? We can as well, because we see a y value of 10, and we see a y value below 10, as well as below 10 here. So we know the graph has to hit a y value of 10 if it's going to connect from y value of 4 to y value of 10. So we can say by intermediate value theorem, the graph will hit the target y value simply because we see y values that's below and above the target y value on either side, and that is called intermediate value theorem. Okay, find the value of the given quantity. Limit as x approaches negative infinity. So we're looking for a horizontal asymptote. The horizontal asymptote, as we approach negative infinity, has a y value of -6. For part B, x approaches -4. So if we approach -4 from the left side of -4, so we see the graph's continuous. From the left side, -4 will be 1, 2, 3, 4, -4. Sorry, so it'll be at -3. So the graph is continuous. So if the graph is continuous, then finding the limit or one-side limit is going to be the same thing as finding the ordered pair there, as long as the function is continuous. Approaching -2, so approaching -2, we see -2, the y value is connecting through +1. For D, we're simply looking for the ordered pair, so h of 0 is equal to 2. We don't care about the behavior of the left or the right branch. We only care about the ordered pair, so h of 0 equals 2. If we approach 0 from the left side of 0, we see that the y value is approaching +2. Okay, for F, approaching 0, in order for a limit to exist, the graph has to approach the same y value from both sides of the target x value. In this case, one side is approaching 2, the other side is approaching -1, so we say the limit doesn't exist. Approaching 3 from the right side of 3, so from the right side of 3, we see that the graph is approaching -4. The graph is continuous through that point, so it's the same thing as finding the ordered pair there. Approaching 4, so if we're approaching 4, that's a vertical asymptote. The limit doesn't exist. However, we see that both branches are approaching negative infinity, so we can say that the limit doesn't exist, but to be more specific, we can say limit is approaching negative infinity from both sides of 4. Approaching +8, so +8 is this hole here. So however, the graph does connect on both sides of that hole, so it does connect to the y value of 3. Approaching infinity, if we approach infinity, we see the graph is going to level out at the y value of 8. Okay, last part, sketching a graph of the function that satisfies the given values. If you want to sketch a graph where the limit as x approaches negative infinity is equal to 8, that means we want a graph to have a horizontal asymptote at 8 as we approach negative infinity, so that's where this graph is showing. F of -5 equals 3, so I'm just going to plot that ordered pair, -5, 3. Limit as x approaches -5 does not exist, so we want the graph to not exist at -5. Either we can have vertical asymptote there, we could have a graph that there's disconnect, so there's a lot of options of what can happen here. We just want the graph to not be connected at that point. Limit as x approaches 1 from the left side of 1. So from the left side of 1, we see that the graph is approaching a y value of 3. Limit as x approaches 1 from the right side of 1 is equal to -4. So we want from the right side of 1, we want the graph to connect to -4. So that's what I have here. Approaching 3 is infinity. So as we approach a vertical asymptote, we want both sides of the graph to approach +infinity. Approaching +infinity, we want the graph to have a horizontal asymptote of -4. So I just sketched that graph over here as we move towards the outer edge of the graph.